when the software license, if the cloud provider provides the service, they must have a license for it, because you're not allowed to install it on a computer without a license, are you? Yeah, most vendors have got bulk licenses. You'll find any large organization will have a deal. So, for example, Google provide Microsoft platforms. They'll have a massive bulk deal with Microsoft where they just can have any number of installations. They just pay them so much. Yeah, it does make sense. So big companies, they don't want to have to worry about individual licenses. They'll just say, we're going to have something in the order of several thousand or several hundred, and now just Microsoft will say, okay, this is how much it's going to cost you. That's it. I would say one thing about the Google Cloud Platform. The user interface that we use through the web page has a habit of changing. My friend and colleague, Randy, who we collaborate on this course, I was asking him today, how do you delete a project on Google Compute Engine? And he said, oh, the UI changed 2 days ago, I'm not sure. So we both had to search for it. So do expect the UI to change somewhat. Google has a command line API which doesn't change, but the web page does tend to change. Okay, good question on Docker. Today's lesson is basically about Docker, so I'll be talking a lot about Docker over the next 4 hours, okay? So it'll be more than an overview you get. Okay, so any other questions before I move on? Okay, we're good to go then. So what we're going to do now, lesson 2, is on virtualization and lightweight containers. And so we're looking at the whole concepts of virtualization, but most importantly, we're going to look at lightweight containers. And in particular, Docker is one of the major implementations of lightweight containers. It's not the only one, but Docker seems to have got themselves into a nice position in the market. So let's, where's my mouse gone? Because I've got 3 screens here, I'm never quite sure where the mouse is, right? So what we're going to do is look at the principles of virtualization. What is this all about? Then we're going to look at how Linux supports virtualization, which is actually very important. This has been the enabling technology. Adding support to Linux for virtualization enabled the other technologies. Then we're going to look at Docker. What is Docker? And we're going to look at Docker's images and containers. So actually, Docker is going to be a bit of a thread throughout the course itself. So this won't be the only time you'll see Docker. There are at least 2 or 3 other sections later on in the program where we look at other aspects of Docker, because Docker is quite complex. We're going to set up a Docker registry, which is important. That's where you use to store the images. And then look at a Docker machine, which enables you to create and control remote instances. The idea being that you don't have to go to different machines to set up Docker. You can just do it from one central location. So we'll be looking at several different aspects of Docker in this lesson. So we're going to look at virtualization, what's the need for it, and what implementations have we got. So what is the problem? Well, typically in the old days, or the traditional way of doing things, a particular computer, a piece of hardware, had a single operating system running on it, and then the operating system had a number of applications running on top of that. So what we want to do is make better use of the actual hardware. So we take the hardware, we put a virtualization layer inside it, on top of it, and then we can run a number of different operating systems or a number of different copies of the same operating system on the same physical machine. And you'll probably find that many of the desktops you get in a place of work may well be virtual desktops, because that's the way a lot of companies have gone. So we've got a versioning problem, and this is that you might want to have applications running on multiple platforms, and they want to run on different operating systems. Some say require Linux, some require Windows, some require OS X, and different versions of the same operating system. You'll find, for example, that some things will not run on certain versions of certain operating systems. So, for example, as we'll see later on, Docker only runs on Windows version 10, and only certain versions of version 10. And there's also a dependency problem. you have applications which are dependent on a third-party library of some kind. Whatever that party might be, it might be something like an encryption library or a graphics library or whatever it happens to be. If you get two different applications which both require a different version of the same library, it's very difficult to have them both on the same machine because you're going to get conflicts, because typically you can't have two versions of the same thing on many installations. So that's the sort of situation we've got to deal with. So graphics libraries, media libraries, they've got different versions, and certain applications require certain versions of each library. So that's a problem we need to consider. So we could have separate environments, but that's going to get complicated. We've got to have a development environment, testing environments, production environments, all different ones. And we don't really want to have different installations on different pieces of hardware. For a startup, it's going to be expensive. You're going to have lots of different pieces of hardware all tied up with a particular piece of software. Then all the combinations of operating systems and dependency libraries just gets completely out of hand. So we need to solve that problem. And this is where we're going, which is a very important aspect of the DevOps environment. We can solve these problems in a very simplistic and elegant way. So in a large organization, the computing requirements are very different. So, for example, everybody might be running the same version of Windows. Say, a lot of companies are still using XP, aren't they? Because they don't want to move to anything later. But the problem is, different roles in the organization need different configurations. So somebody in a sort of admin role will probably only want a basic installation with word processing software, like Microsoft Office or something like that. Developers need compilers and all developers development tools, IDEs, and access to all sorts of things. And so you need different specifications of software combinations for each individual employee, technically. So that makes it difficult because you've got to roll out the environment. A new employee starts. They've got to get an environment. It's got to be the right one for their role. Then you've got the problems of updating the software and applying fixes and patches to the operating system. Then what happens if you want to have a meeting and do live demonstrations? That's a bit of a pain. You don't really want to cart your laptop or your desktop computer, even worse, into the conference room. Although a laptop can help this sort of situation, but then even then you've got problems with versioning and what you can and can't put on a laptop within the organization. So the next approach which came along was multiple boot machines. So have multiple operating systems on the same physical hardware, but they all typically reside on a separate disk or a separate disk partition. That requires a complex boot manager, of which there are several around. You're probably familiar with Grub, which is the one of choice for most Linux distributions these days. Grub's quite actually easy to configure. I was having to play with it myself today. I installed a version of Debian 8.7 Linux on a spare laptop I got, and the first thing that happened, I lost the root password. And I had to do a root password reset, which is not easy. I hadn't done one for quite a long time. It didn't take very long, but Grub was the way to get there. Okay. There's other problems associated with things as well, or issues. If you have a Linux distribution sitting alongside another distribution, such as, say, a Windows or any other operating system, the chances are that Linux will be able to read the operating system's disks, because Linux has got drivers for reading all sorts of different formats of hard drive. And so you've got a complete compromise of security. The operating system thinks it's securing its disks, but in fact, Linux can bypass everything. In fact, if you boot a Linux system on a DVD or some other bootable medium, you can do all sorts of horrible things to any machine because the Linux will just be able to read anything it likes, grab files, anything. So now we have the concept of a virtual machine. Now, it's quite interesting in this day and age. We think we're pretty advanced in terms of computing power and all that sort of stuff. But in terms of software, we actually haven't come a long way. Virtual machines and lots of other technologies, we start throwing these words around, like RESTful web services. Are they new? No, they're 20 years old. Virtualization, is it new? No, it's 45 years old, no, 55 years old. Okay, it's really quite old because early mainframe computers used a form of virtualization to do multitasking between programs. Effectively, what happened was each program had to appear to have full access to the machine, and so a virtual environment was created for that. So early versions of operating systems, which I think going back to say 1980s, had the word the letters VM in them somewhere or another because they were actually running virtual machines. And then what happened was in the late 1990s, Intel produced the 80386 CPU, which was the first proper CPU, if you like, that could do proper multitasking as we know it today. And if you knew what you're doing, you could take an 80386 CPU and you could switch it into what's known as protected mode, and then you could access a number of virtual 8086 virtual machines. I actually remember doing this. Windows used to take over the machine. It wasn't using the full capability of the 80386, it was using it in what was called real mode. I wrote an assembler program in Windows, which I ran. What it did was it executed some disassembler code. It created a data structure and pushed the machine into its full-blown protected mode. And then what I did was I dumped the Windows operating system into a virtual 8086 environment, and it was quite unaware of it. And at the same time, I had a little command console at the bottom of the screen where I could type commands and play around with things. So that's been around for a long time. So the 8386 allowed you to do this kind of stuff. VMware, which you may have heard of, is one of the big players in virtualization. And they started around about that time. And they've been building virtualization software and platforms ever since. So what actually is a virtual machine? Just to put that in perspective, if you think about it as a partition, you take all the hardware resources you've got and partition it in such a way that you can install an operating system on part of those resources and they can't see each other. And you have some underlying software, which is the virtualization layer, which controls everything. It's like it is probably an operating system in its own right. Almost certainly the virtualization software is going to be based on a Linux kernel. So they're great for setting up well-defined environments. Virtual machines are basically a collection of files. They tend to be rather large files, but you can simply copy these files around and just run them on the machines. All you need is the virtualization software running on the host operating system. You can run several different operating systems on the same machine at the same time, all running as virtual machines. And so we don't have multiple boot machines anymore, really. We don't really need them. You can use virtualization to do so, especially with recent advances. So in terms of virtualization software, there are basically two types. There's a type 1 and a type 2. The virtualization software is known as a hypervisor, is the name for it. And what it does is it gives the guest operating system access to what it thinks is hardware. It may be the real hardware, or it may actually emulate the hardware in some way. That can solve some quite nasty problems. So a type 1 is called a native or a bare metal hypervisor. You install the hypervisor as the main operating system, if you like, on the hardware. It's typically based on Linux, because the Linux kernel has got all sorts of good stuff in there for doing it. In fact, there's a thing called KVM, the kernel virtual machine, which is part of the Linux kernel, which enables virtualization almost for free. And then what you do is you run your guest operating system effectively as a process on the host. It's a little bit more than just a single process, but it's a kind of a partitioning. And these are normally for the high-end servers. So if you've got a data center, you'll be using type 1 hypervisors. So you've got Oracle VM Server, Citrix, XenServer, VMware ESX is a popular one, Microsoft Hyper-V is another one. They all do the same kind of thing. So this is the diagram. You've got the hardware, the hypervisor sits on top of it. Then on top of that, you've got a number of operating systems, and each operating system runs a number of applications. So that's the kind of tree structure we've got. So a type 2 hypervisor or a hosted hypervisor is basically a program running on a conventional operating system, and what it does is it does the necessary mapping. So when the guest operating system makes a system call, it goes to the hypervisor software, which then maps it onto the host operating system calls. So it kind of acts as a mapping layer between the two. It's used on desktops and laptops, and that includes the likes of VMware Player, VMware Workstation, Oracle VirtualBox are technically type 2 hypervisors, although this is a bit blurred, as we'll see in a moment. So a type 2 hypervisor looks like this. You've got the hardware, you've got the operating system, you run the hypervisor as some kind of application, and then that hypervisor then runs a number of operating systems, which in turn run a number of applications. So that's the type 2 hypervisor model. It can cause a few problems, particularly performance, because one thing you haven't got any control of is the host operating system. It can take resources which you just can't free up. So the technology, the way it's evolved. So the 8386 I mentioned before could virtualize the 8086 processor, which predated it. Basically put it in a different mode, and it was a very easy way of doing it. You just set up a container for it. Then some important developments happened. The chip manufacturers, typically Intel and AMD, what they did was they started to add extra instructions to the CPU, which are the virtual machine extensions or VMX instructions. And then also very important, the virtual machine monitor, VMM instructions. Sorry, the virtual machine monitors, the software which enable you to access those VMX extensions. The VMX extensions basically allow you to get control of the CPU in a more powerful way than the normal operating systems do, because these instructions, when activated, effectively undermine the existing operating system. So you have a virtual machine monitor, which is basically a type of hypervisor, which invokes these special instructions, and then it allows the multiple operating systems to run in virtual parallel. So what happens is, typically you've got the host operating system, and then you've got the VMware Player or something, the hypervisor program running. What happens is that the hypervisor program invokes these special instructions, which puts it in a special ring of control, which is underneath the host operating system. Then when it runs another operating system, effectively the host operating system and the guest are running in parallel, and they can actually access the same hardware, and they can share the hardware. That's an interesting development. So then that was improved even further with the memory management unit, because memory management was difficult, because what you have to do is map memory pages, and this greatly simplified it, and meant that the virtual machines could access the memory directly by remapping it. And then they added extended page tables, which made it even more powerful and solved other memory management problems. And once you've got all these three levels of functionality built into your CPU, then you can do some really clever things in terms of virtualization. So effectively now, the distinction between a type 1 and type 2 hypervisor is very vague. Because if your CPU supports full hardware virtualization, then you can effectively have a type 1, which is a type 2, which is effectively a type 1. You need to check your chipsets. You can find out from the Intel sites and other ones what the facility is. But and also, because of the way that it works, I think you might be able to guess when I said that the virtualization software can invoke these instructions which underpin the host operating system. There's an implication of security there, and you can actually completely compromise security if you know what you're doing. It has been established that that is the case. So by default, the security extensions are switched off in the BIOS, in the firmware. If you're trying to run virtualization, the first thing you should do is go into your BIOS and try and switch it on. Otherwise, your virtual machines will run incredibly slowly. Okay. So now then, we've got virtualization in hardware. The host and guest can basically both use the real hardware. And you've got other things like the KVM is a kernel-based virtual machine built into Linux. The FreeBSD Beehive kernel modules effectively can turn a Type 2 hypervisor into Type 1. So we've got full control. Okay, it's all good stuff. But there are problems with virtual machines. It's not the perfect world, but it's better than having dual boot or multiple machines. Now, one of the problems is the virtual machines are full operating systems, and they're typically installed into the hypervisor via an ISO image or a DVD of some form, normally an ISO image. And then you need to install the application software on top of it and configure it. So it's like installing, which is like exactly the same as installing a complete operating system every time you create a virtual machine. Obviously, once you've done it, you can copy it easily enough, but that's the first setup is like more complex. Then there's other issues. There's a difference with 64-bit and 32-bit. If you've got a 32-bit operating system, your hardware is probably 64-bit these days. Almost all modern hardware is 64-bit. But there are 32-bit operating systems around. So if a 32-bit operating system runs on a 64-bit guest, if you want to run virtual machines, for a start off, you can run a 64-bit guest on top of a 32-bit host, only if you've got the hardware extensions on the CPU and switched on. But there's another problem in that the 32-bit machine will do some memory mapping, and maybe a lot of the memory will disappear and is not available, which means you probably won't leave enough memory left over to run the guest. I've had that problem in the past, that you've only got like 1 gig of memory available for the guest, which isn't enough. The other problem is that the virtual machines are very big. Typically, they're broken into files. So if you've got, say, a 60 gigabyte hard drive on your virtual machine, it'll be broken up into 4 gigabyte files, a whole bunch of them, and they'll just grow as you need to add them. So the 2 gig chunks are for convenience, basically for doing file transfers. But how do you get them to transfer across the internet, for example, or copy them on drives? Have you got a big enough USB stick or drive? Typically what you do is you need to break the virtual machine into chunks and compress it. The program 7-zip is very good at doing this. You can say, right, I want you to take this whole virtual machine, I want you to compress it, and I want you to break it into, say, 1 gigabyte chunks, and then you just transfer the 1 gigabyte chunks one at a time across the network. Then 7-zip will reassemble and extract everything back to the original virtual machine. But it's a bit painful. I've had terrible problems copying virtual machines. It just takes such a long time. So look at some terminology. And we have these terms which are related, but let's make sure we're clear what we're saying. So multitasking is basically any modern operating system which can run multiple programs concurrently. It usually uses some kind of time slicing to schedule the actual processing. You've obviously got more than one CPU these days. Nearly all machines have got multiple cores with hyperthreading, so you'd never really have single CPU machines anymore, which had to do extensive time slicing. So you do get some true parallel running. So multi-core, what's that? Well, that's where you have a CPU, as in the chip that you buy, which has got more than one CPU actually built onto it. It used to be that every chip had exactly one CPU core on it. And what's happened is that the geometries of the chips have got so small now that we can't really make them any smaller. So what the chip manufacturers have done is they put in multiple CPUs on the same physical piece of silicon so that you've got multiple core chips. And typically you get a 2-core or a 4-core machine. That's fairly normal, isn't it? The CPU chip has got more than one core. Then you've got hyperthreading, where every single CPU core can have several instruction pointers. Effectively, it can run 2 threads concurrently. And typically, most cores these days have got at least 2 hyperthreads. So if you've got a 4-core chip, you've effectively got 8 cores, 8 CPUs effectively, which is quite a lot of power. And virtualization is a single computer which you partition the hardware in such a way that each of the partitions looks like a separate computer. Okay. So that's the basics of virtualization. So if we do the knowledge check, what is type 1 virtualization? Virtualization software installed directly on the hardware, a dual boot machine. Virtualization software installed on a host operating system or a special CPU instruction set. Right, we seem to have a good consensus there. Yeah, it's virtualization software installed directly on the hardware. I would say the distinction is very vague these days. So now we're going to look at Linux virtualization. And this is important because Linux was the enabling tool for making the good stuff we're going to be looking at later on happen. And so the Linux kernel, being open source and being very flexible, got lots of stuff in it, it's relatively easy to add modifications to it to do things that are really, very useful. So when we look at tools like Docker later on, although it does technically work on other operating systems, you really need to run it on Linux because Linux has got the full support that it needs. So software installation and management. So you've got the problems of multiple applications running on the same machine, may not be compatible. They've got shared libraries which are different versions. If you need to upgrade the dependency for one application, you might break the other ones. When you remove an application, do you remove the dependencies or do you leave them behind because something else might be using them? So there's all sorts of issues. If it's a dependency no longer required, can you take it away or not? We've got the packaging tools like RPM for the Red Hat, CentOS family of Linuxes and APT for the Debian Ubuntu flavor of Linuxes. They help a lot because they package the software and they've got clever installation and removal software which can handle the dependencies quite well, but they still get some dependency issues. And you can inadvertently pull in a lot of stuff you don't actually need. So, for example, I wanted to install Maven on a particular machine. I used APT to do it. It pulled in all sorts of rubbish I really didn't want, so I had to remove it all and install Maven manually because it was the dependency rules for the package was too complex. So we've got the term Unix jails. You might have heard the term jail. In the world of Apple with iOS, you might have heard the term jailbreak. Basically, all mobile phones effectively implement jails because all the applications on the phone are effectively isolated from each other. It is particularly true of iOS, less so of Android. And if you want to get outside of these containers, you need to jailbreak your machine, which requires quite a nasty hack, but it can be done. I've never quite had the courage to do it on iOS, and I wasn't able to do it on Android, but I know the principle is fairly easy because I managed to break the root password of a Linux machine in a few minutes a day. So what happens is that Unix has had a facility to confine applications. There's a mechanism called chroot. What it does is you can say to a program, okay, when I run you can only see this small section of the file system. It's very commonly done for things like web servers and other services. You don't want the web server to see the whole of the hard drive on the machine because if something goes wrong, it could potentially dish all the files out, serve them all out as web content. So you use the chroot mechanism to put your web server or your DNS server into a well-contained place. And that gives you a means of isolating processes and dependencies. You do, of course, have to put all the dependencies into the isolated area, which is a bit of a pain. But it is actually possible to get out of jail because the chroot mechanism has a well-known loophole for getting out. And so it isn't absolutely perfect. So what's happened is that another set of technologies was introduced, which are called container technologies, which enable you to make more robust jails, which are hard to get out. Okay. So that's one thing. One of my next projects is going to be seeing if I can get out of the Docker jail. So it's going to be quite an interesting challenge. And this is known as operating system level virtualization. You basically have an application which has a limited set of resources available. And what actually happens is instead of having a separate kernel for each OS or each application, you have a single kernel and all the containers run as children of this the main kernel, which is really good. So how does this work? Well, there's several things that were done. First of all, Linux introduces the concept of namespaces. And a namespace is a wrapper around some kind of resource. So, for example, processes can be put into namespaces. And what happens is that every namespace contains a number of processes, and it looks to them like they've got their entire own instances of some kind of global resource. And it's an important means of implementing this. So basically what you can do is you can create namespaces and you can move processes in and out of namespaces on the fly. So a running process can be moved from one namespace to another. And this controls exactly what resources that process can see. So Linux introduced a number of namespaces. Now the first one, C group, is the most important one, because this is the control group, which is the key that underpins the virtualization mechanism of containers. We've got IPC, which is for inter-process communication. That's shared memory and sockets and things like that. We've got network for network devices, so you can create virtual networks. We've got mount, which defines mount points, which are external volumes like disks. We've got process ID, which is also a very important one. You can group process IDs together so that they can't see each other if they're in a different namespace. You've also got a namespace for users and groups, as in the login users and groups. And then you've also got the Unix time sharing group, which is not really used anymore. It's if you want to change your host name, which is something you don't really want to do very often, if at all. So control groups, what are these? The idea is a control group is a partition of resources. It started with Google. Google seemed to have innovated a number of things in 2006. And they started a project called Process Containers, which was an extension of the Linux kernel. The Linux kernel team merged these changes into the 2.6.24 kernel, and it's been there ever since. So what happens is that a control group will contain a number of CPUs and a certain amount of memory, and then into a control group you put a number of processes. So for example, in that case we've got the control group which has got CPUs 6 and 7, another control group has got CPUs 1, 2, 3 and 5, so that any process that's in control, the group 1 web, will only have C2 CPUs. Any process that's in C group, in group 2 DB, will see 4 CPUs. Likewise, the memory is allocated in a 3-to-1 ratio, a 2-to-1 ratio across those control groups. So it means you can partition the actual resources like CPU and memory, network devices and other things like that, and then into these control groups. Then you put the processes into the control groups, and they only see a restricted part of the full system. It's all controlled by the single kernel, which is the host operating system. Control groups can be in a hierarchy, and so each hierarchy can be attached to a number of subsystems, which are pieces of functionality, and each control group inherits from its parent. And so the C group hierarchy is a partition of the process in the system. What that means is that all the processes in the system belong to one single C group, and each process is in a single C group. And processes start in the same C group as their parents, but they can be moved around. So, for example, you can start a container up, and then you can start the process and then move them into another C group, so they've got different access to the program that started them, which is how these containers work. Now, to run the analogy, if you think about Linux processes, they are also organized into a hierarchy. Every process in Linux or Unix has a parent process. And when a process is started by a fork operation, where basically the parent process address space is copied and a new program is run, the child process receives a copy of the parent's environment variables, signal handlers, and open file handles, which it can do what it likes with. And so we've got this idea here. We've got the parent process as a fork which copies itself, clones itself, if you like. Exec runs a new program inside that memory space. When the child process exits, it becomes what's known as a zombie, and then the parent process must do a wait operation to clean up the mess, and that gets rid of the zombie process. That's the kind of process lifecycle. Now, the processes are in a hierarchy. At the root of the tree is process number 1. It's normally called init, and it's the first program that's run by the kernel, and every process is a child or an ancestor of the or a child or a grandchild or whatever it is of the init process. If the child's parent process dies before it dies, its parent becomes init, process number 1. So now we get to containers. Containers, we say, are operating system level virtualization. So the model is slightly different. We've got the hardware, and we've got the standard operating system. Well, let's say it's Linux for the time being, because that's where it works best. Then you've got your virtualization layer, which is going to be something like Docker. And then you have these concepts of containers. And the Docker program orchestrates the containers. A container is basically a cut-down file system, a Linux file system. It's got all the files needed to run typically a single application. But they're completely isolated. So container 1 can't see inside container 2 or container 3, like the other way around. The only way the containers can communicate with each other is across the network or across a shared file system. So typically what will happen is each container will contain one piece, such as say a database or a web server, and your application in the container world will consist of a number of containers which are orchestrated together. And it's a great way of doing things. Cloud computing utilizes this quite extensively. So the cloud environments do like to use this thing. Google's got Google Container Engine, which is one way of implementing it. Or alternatively, you can simply run a Docker Swarm, which is where you run Docker across several machines. Then you run containers across the machines, and they can all talk to each other to build an application that way. So how does it work, hang together? What you've got is the hardware is controlled by the Linux kernel. All the kernel is basically a wrapper around the hardware. That's what a kernel's job is. It just provides a single interface to whatever hardware is there. In basic of a Unix, Linux, the interface looks like a file, no matter what it is. The kernel controls the namespaces and the control groups. It may have our old friend SE Linux, which is the security enhanced Linux, which can cause more problems than it's worth. Getting it to work properly is difficult. Getting it to cause problems is easy. So we'll quietly ignore SE Linux for the time being. But basically, the kernel manages the namespace and control C groups. You've got the management interface, which then controls the containers. Effectively, what it does is it installs the containers as part of the file system, but it's a self-contained unit. It uses the namespaces and control groups to isolate it. Then it runs a program inside each of the containers in its own namespaces and C groups, which controls the way that the isolation works. Effectively, it's a chroot environment inside the container, and the control groups enforce the constraints those resources like CPUs and memory and network devices and other things. It's quite a neat system. So here we got an example of operating system virtualization. So we've got these containers with they've got a file system, it's got binaries and libraries necessary to run the program. You've got some kind of tool. The Linux containers XC is a set of tools for controlling the namespaces and control groups. There is a thing called LXD, which is a container hypervisor built on top of LXC. It's actually designed by the Ubuntu group, and it is a form of container hypervisor. There's also Docker, which is a hypervisor built on top of, it's actually not LXC because they rewrote it. So they've got their own bespoke version of the management tools in Docker. There's also another one called Rocket, you might have heard of. It's associated with CoreOS. That's another one. So if you build an image from Docker, LXD can run it and Rocket can run it. So they're all interchangeable, because all a container is a cut down file system with all the libraries and executables needed to run an application. All you need is a supporting kernel and one of these tools like LXD, Docker, or Rocket. Yeah, I think you can even do it with LXC actually, but it's a bit more painful. Now, this is where it gets really neat. There's a concept of a union file system, and it's been around for a while. It's available for Linux and the various BSD flavors of Unix. And what it is that you can effectively have a file system which is layered. You can put a layer on top, so effectively you can merge things. So what you do is you start off with a base layer, which has got certain files installed on it. Then you overlay another layer on top of it. And what it does is effectively it forms a union of the two. So if you've got the same directory on both with different files, you end up with the same directory with both sets of files. There is a hierarchy that if you get two exact file paths the same in two layers, the one on top takes precedent. Or you've got some ways of giving it a priority as well. So what you do is you build up your file system in layers, like an onion, sort of building up these layers. And they're called branches. And they can be read-only or read-write. So typically these are used extensively. Containers are always built from these layered file systems. You start off with something basic, like a flavor of Linux, and then you add a layer of libraries, and then you add your application layer, and then you maybe add your data layer to it. And then finally you add a writable layer and then execute it. So it's a very powerful mechanism. And you can do some really clever caching as well. So the idea of this is then you can have a read-only file system and then put a writable layer on top of it so that you can write to the file system. You can't change any of the files, but you can hide them. So you might have heard of Knoppix. It was a cut-down version of Linux. You basically could run it on a memory stick or a DVD image. But obviously that's read-only. So what it did was it put a writable layer over it in memory, which enables you to create files and make changes on top of it. So you can have these layered images. So that's the enabling technology. So what is operating system level virtualization? Is it virtualization software installed on the host machine, a dual boot machine, a host operating system with a guest operating system, or kernel support for multi-isolated user space environments? Okay. Getting a number of different ones. It is actually D. It is a kernel support for multiple isolated user space environments. There is a bit of A involved because you do need the software that can invoke it. Okay, so but technically it's the kernel support for these namespaces and control groups which enable you to do these things. So let's have a look at Docker. So we've got, say, there's a number of different container management tools. There's LXD, there's Docker, and there's Rocket. Docker, I think, have kind of rushed themselves to get to a good place in the market, and they're gaining a lot of attention. Though I must admit, I was a little shocked when I was playing around with Docker recently. I found some rather serious security problems, which I actually reported one of them to the Docker team, and they said, "Oh, that's normal behavior," and I was a little shocked about that. But never mind. I'm going to have to investigate this in much more detail. So, what is Docker? Well, basically, it's a software containerization platform. It's basically you've got a Docker daemon, which is a process which runs, and it enables you to create and run Docker containers. That's what it's all about. So typically, it only worked on Linux, but a Docker container typically starts off with a base Linux operating system, and it can be based on any of the popular operating systems. People have actually made various cut-down versions. You don't want the full-blown operating system with all the files and stuff. You don't want all the boot scripts and all that nonsense. So you can get a base image, which is, say, for Debian or Ubuntu or CentOS, any of the popular operating systems, there's a base image. There's one that's really interesting called Alpine. Alpine is a really, really cut-down image. We're talking sort of like the other ones are in the order of large numbers of megabytes. Alpine, we're talking kilobytes. It's really small and really compact. And so what it does is Docker provides the boundary, the jail for running it. So it means that you can't get out of it. As I say, I think the story is still open as to whether it is possible to get out of it, but there are ways you can influence the outside world, I know for a fact, but as to whether you can really get out of it, I'm not sure. So the Docker image is a foundation for any container. So what you do is you, as we'll see later, you take a base image, you add layers to it to form another image, which is the image is a read-only copy. Then when you create a container, it puts a writable layer on top of it, and it's executed. So that's the difference. So basically what you've got is the normal operating system with its kernel, and then you've got Docker, and then you've got any containers that are managed by Docker. So Docker was originally for Linux. It really still is. It requires the kernel container functionality, which means you've got to have a Linux kernel above that minimum level where it was introduced. It has to be 64-bit, and so now it has to be a version 3.10 or higher to get it to work. And it runs on most flavors of Linux. For some, you can get it with an RPM or APT package. Others, it's a little bit more painful. There's usually a way of installing it. If you go to the Docker website, it gives you instructions as to how to install it on each of the operating systems. Some it's very trivial, some requires quite a lot of work. But it's a one-off thing. Once you've installed it, it's fairly straightforward. And actually, once you've got it on one machine, you can actually use Docker Manager to get it to install on other machines. Although I've had a few problems with CentOS and Docker. Yes, good question. Docker containers use networking to communicate. It's actually, there's only two ways a container can communicate with another container, by a network or by a common shared volume, some kind like a disk space. The containers have their own virtual network interface cards. So basically, to give you the full story, when Docker starts up, it creates a virtual network inside its environment, which is completely separate from the network that the computer's on. There is a gateway between the host network and the Docker internal network, which Docker manages. Whenever it starts a container, it uses typically DHCP to give it an IP address on that internal network. So all the containers running on the same machine, by default, are on the same network, but they can't see outside that network by default. That's an interesting question. Does Docker do the job of Jenkins? No. Jenkins is an continuous integration tool. Docker is purely a container management tool. To put it in perspective, later on we'll be finding this out. You can download a Docker container containing Jenkins. Yeah. So if you want something like Jenkins or any other application, you can get containers with them on. So yes, it's the host, then the Docker virtual machine system, and then you've got the Docker containers managed by the Docker environment. It'll become more apparent as we go on, but it's just, yeah, there's quite a lot of pieces to it, aren't there? So Docker for OS X. Will Docker run on Windows 7? Not natively. There is a way of doing it. Basically, you can run Docker in a virtual machine. No, as I said before, Docker is not the only tool for container management. LXD and Rocket also do it. Argue Rocket may be better. It's something I've got a project underway at the moment to investigate all this technology and exactly where everything stands, because I need to figure out a few things about how Docker works, because as I say, I found a security problem that I'm rather unhappy about. So, okay, so for OS X, they didn't support OS X directly until earlier last year. I'm forgetting we're in the new year now, aren't we? It was about the middle of last year. They introduced a native version of OS X built on the X-Hive hypervisor, because OS X is basically a flavor of BSD Unix. You have to have a fairly recent Mac, because it has to have a CPU with the memory management and extended page table support. Otherwise, it will not work. And you need to have at least the Yosemite version 10.10.3 and at least 4 gig of RAM. It does work, and I have got it installed on my Mac here, but networking is badly broken. So it is supposed to be the case that the Docker daemon process listens on a TCP IP port for incoming network connections. The OS X version does not and cannot. There is some kind of problem between the Docker guys and Apple, where Apple won't release the necessary information to be able to do it properly. I've found it very frustrating. So if you've got a Mac, you can install Docker on it, you can run containers locally, and the containers can talk to each other locally over the network, but you cannot communicate with an external Docker implementation from OS X directly. So that's why I've been installing Debian Linux on a separate laptop. So I've got a full-blown Docker that actually does work. Yeah, the networking is terrible under OS X for Docker. Docker for Windows, again, there wasn't one available until the middle of last year. It now is supported. It requires certain versions of Windows 10. They say they might extend it to other versions. The limited network support, yeah. Under Linux, it's no problem at all, ever, because the Linux networking just works. I'm not sure the full story about Windows, because I've never tried it, but certainly OS X, the networking is quite badly broken. So the Docker for Windows requires certain versions of Windows 10. It requires you to install the Hyper-V package, which is the Microsoft hypervisor package. And that means that you can't run VirtualBox. If you've got Hyper-V installed, VirtualBox will not work. And basically, it provides a virtualization environment and makes Windows look a bit like a Linux kernel to make this work. It's a bit of a hybrid approach, actually. Now, for other computers, the Docker Toolbox. Now, this was how you used to run it on OS X and Windows before the middle of last year. So if you don't meet the requirements, then you use Docker Toolbox. What Docker Toolbox is an Oracle virtual machine with Docker installed inside it. It basically runs a Linux operating system with Docker installed on it in a virtual machine. Okay, but that does work properly, and it'll work well. It'll do the networking and everything because effectively you're using a Linux virtual machine here, and that solves the problems that there were with Docker. So Docker is client server. It's got a client called Docker. Yeah, the toolbox will definitely work on Windows, even Windows 7. As long as it's 64-bit rather. Any version of any 64-bit operating system that can run VirtualBox can run the Docker toolkit, which is the way around it if you haven't got available Linux box. So I've got a few spare laptops, and I've just installed Linux on it just for Docker. Oh, and by the way, the Docker client on OS X will talk to a Docker server on Linux because it can do the networking. It's just the server can't do the networking. So the client uses a RESTful API over HTTP. It prefers to use a local Unix socket. You actually have to enable the HTTP explicitly on most systems to make it work. It doesn't listen on the TCP port by default. So you've got the Docker daemon that does everything. It does the building, the running, the distributing, downloading, everything of containers. So the client just basically tells the daemon what to do. There's also a registry, which is where Docker images are stored. They can be in Docker Hub, which is a central one. You can have your own private one, or the certain vendors also provide registries. We'll look at those in more detail later on today. So, got to understand here, this is a very important distinction. We have the images and the containers. So a Docker image is like a read-only template. You start off with a base image, which you normally download from Docker Hub. Because you could build your own, but it's painful. Then what you do is you add layers to that image. And how you do that, I'll come back to. But what you do then, given an image, you can create a container. So what happens is you go to Docker, you say Docker run, and give it an image. And what it'll do is it'll take that image, copy it, put another layer on top of it, which is writable, and then executes a program which you can specify or use the default one, which happens to be hard-coded into it. That runs as a container. The container can be started and stopped and do all sorts of other things. And then what you can do is once you've got the container, you can add software to the writable layer of the container. And then you can stop the container and save it as an image. So that's how you add layers to an image. You take an image, make a container from it, install software into the writable layer, and then save it as another image, and build up the layers like that. It can be done in several different ways, but we'll be doing both of those ways. But remember that containers, if you delete a container, the writable layer gets destroyed. And so the only way you can save it is if you actually do what's called a commit. Yeah, basically every layer is saved as a separate file, all the images are composite. If you download an image from, say, Docker Hub, and you say get the Jenkins image, you'll find that it's got about 20 layers. So what it's done, it started off with a base layer and added all these extra layers on top of it as it built up the application. So when you make a container, add some files to it, and commit it, it'll create another layer which becomes associated with a new image. Yeah. So containers can be started, stopped, run, deleted, and they often have various ways of configuring themselves. It's quite powerful. It's quite a neat system. Just have to put all the pieces together to get to grips with it. So it's the union file system. I've already described basically what happens here. You take a base image, create a container, install software, save it as a layer, and make another image. Docker Hub is a repository in the net, in the cloud, which enables you to download pre-built Docker images. So if you say, oh, I want CentOS Linux, you say Docker pull CentOS, and it will go to Docker Hub and grab it, copy the image and download it. Okay. You can have your own account on Docker Hub if you want and store your own images there if you wish. So it's basically building up these layers. So here we've got an example. You've got all the layers have really exotic names, which have got big hexadecimal strings. So this is showing that you've got every layer, every image has got a history. Each layer was something added to a base image. So running containers, you've got the Docker run command, and basically it takes an image and creates a container by adding the writable layer. When you give it a run command, you specify an image name. What it does, first of all, it looks in a local repository that it manages for that image. If it finds it, it'll use it. If it doesn't find it, it'll do a pull from a Docker Hub by default, or any other Docker registry you can specify. That means it'll download the layers that make up the image and then build up the image from the layers. And it can take a little while. And you see the process very clearly when you do the Docker commands. Then it creates a new container using the file system on the image by adding another layer on top of it, which is a read-write layer. It creates a network interface if you want one. Assigns an IP address. It basically uses DHCP to do that by default. It may connect input and output streams from your keyboard, and then it'll execute a specified application. And then you're basically running inside the container. So if you want to start a shell inside the container, that's fine. You just do that, and you look like you're inside a different environment, which is the contents of the container. And so all the containers basically run as child processes of the daemon process. I'm not actually familiar with Vagrant. I'll come back to you on that one. So here is the way you do things. If you want to download an image, you do a Docker pull command, Docker pull space, and then you give the image name : version number. Now, every image has got a : latest on Docker Hub. So if you want the latest version, you specify : latest, or otherwise you specify a specific version number. So pull guarantees it's there. If you just do a run, Docker run CentOS : latest, it will do a pull if it doesn't already exist on the local machine. And what you can do there, what this is doing in those last 3 lines, is Docker run CentOS latest, who am I? So it'll start up the container and execute the who am I command and then terminate. So the image, the container will stop when the who am I command is finished, and the output of the who am I command will appear on your screen. Likewise with PW and D and date. Okay, so that's the Docker run command. So if you want to run a container interactively, which is actually very useful to find out whether it's working or not, you use the -I and -T switches to keep the stand input open, make it interactive, and allocate a sudo tty device. I normally just type -IT. You go Docker run -IT, CentOS : latest, and then a command. And so /bin/bash will run the bash shell. What will happen there is you'll get a root prompt from a bash shell, and you are inside the container. So you can use all the commands that are available within that CentOS image to look around the container. And the moment you exit the bash shell with Control-D or exit, the container will stop running. It doesn't go away, it stops running, that's all. If you want to find out what containers are running on a machine, you use Docker PS. And you can also do the stats command, Docker stats, which you'll find tell you what the container resource usage is. It gives you a continuous thing. You have to do a Control-C to exit it. Docker PS is very useful whilst running. Now, when you run a container, it gives the container a name. And the default name, it makes up something rather odd, some kind of comical name like Hungry Lumiere or whatever it is. It's different every time. So what I always do is do docker run -it --name and then a sensible name for the container. Because what happens is that when you want to do any operations on the container, like stop it or remove it, you need to give the name or the ID. The ID is a huge hexadecimal string, which you really don't want to deal with. Let's copy and paste. So giving it a sensible name means it's easy to find. You can do Docker PS to find it, but it's easier if you've given it a name. So in this case, you run it like that. If I did docker stop CentOS from another window, it'll stop the CentOS container. And notice, some people get confused one thing. You cannot run Docker commands inside a container. So you need to be aware whether you're in the container or outside of it, because Docker is not installed inside the container. There's also a Docker PS-A, which lists all containers, including stopped containers. And Docker RM container name removes the container, deletes the container, which means that anything in the writable layer is destroyed. As a Docker RM-F also will stop a started container and then delete it. You can also attach a container. This is rather an odd thing to do, but it seems quite interesting. If you run a container like this first command, which is running a shell, bash, then on a second terminal, you go docker attach CentOS. You'll get a second terminal session to the same container with the same content. So if you type a command in one terminal, you'll see the command and its output appear in the other terminal at the same time. So both sessions see the same inputs and outputs. And you can detach yourself using Control-P, Control-Q if you want to do that. Something you don't normally do like that, but you can attach to a container which is disconnected. You haven't got anything connected to it interactively. So the Docker stop stops the container. Normally containers run in the background as daemon processes, so that's when you use the stop command. It's also, you're going to do a stop -T, which will do a timeout. Now, interestingly enough, the main process is process ID number 1. Now, process ID number 1 in Unix is always in it. In a container, it's the one you executed, which may be a shell or it may be an application. But it's always process 1. And it's sent a sigterm and then possibly a sigkill if it doesn't terminate within the default time period. That kills the container effectively. That stops it. It doesn't remove the container, it just stops the application. You can restart it if you wish. You can also pause containers, something I don't tend to do. It doesn't use the sigcomp mechanism because the process is the visibility of the signals. It uses a cgroup mechanism for doing that. But you can pause them and unpause them if you wish. Yes, good point. Docker, you could do docker --help, or you could do docker run --help, or docker images --help. You can use that for anything to get a list of all the commands and their options. A pause where you stop the container, put it to sleep. It just stops it immediately, and then you can wake it up again later if you need to stop it temporarily for some reason. So you can do docker start, and you can reconnect an interactive session if you do that. So you can do a start or attach. Removing containers, you use docker rm and the name of the containers. If you do -f, it will stop a container. If you do a docker rm on a running container, it will not do it. You have to force it, or you do a docker stop first. A quick way of getting rid of all the containers is if you do docker ps -aq, it doesn't do a full listing like it normally does. It just lists all the container identifiers as a big list. So if you use command substitution, docker rm $ brackets docker ps minus aq, it'll delete every single container on your machine, which is a quick way of cleaning everything up. And most often, you have your containers running a service, so they're daemon processes. So you do docker run -d, and typically name them as well. So if you're running an nginx web server, do docker run -d -- name web server nginx. And you can also do a docker kill if you wish to do that. You can do a stop as well. Okay, so that's a flavor for Docker. Now, Docker is installed on our virtual machines that we installed yesterday. So what I'm going to do now is give you a URL to get you to the instructions for this lab. So again, we're going to be using the Google Cloud instance we did yesterday. So Docker has already been installed and it's up ready to go. So just what you do is have a go at connect to your virtual machine using SSH, use the various Docker commands to try out a few things. So just have a play around with running containers, trying different things, and see how you get along. So it's going to be, I think this exercise will probably take about half an hour. So we'll allow half an hour for this. If you can let me know when you're finished, or message me if you've had any problems or when you're finished, okay? Okay, so that's the first installment of Docker. There's quite a lot of questions there. I know you're very keen to get onto more of it. We'll cover some of the things that you've been asking later on because we've only just really scratched the surface of Docker, what it does, building images, all that comes in the next sections as we go along. Okay. To answer the question on Vagrant, Vagrant actually sits on top of virtualization. It's a development environment for controlling the various versions, so it sits on top of the kind of concept of things like Docker. Right, so that's Docker and the basic commands. Use Docker -- help. I don't know if you did a Docker images and compared the size of Alpine versus Debian. It's a lot smaller. Alpine is tiny, so it's good for building really lightweight applications. If you can get away with the minimal amount of software that's installed on Alpine, it's a good base image. You don't need all the heavyweight stuff that the main distros like Debian, Ubuntu, CentOS actually have available. It's not necessary. So we have a knowledge check for that. So what's a Docker image? A running software application, a read-only template containing complete software application, complete operating system, or a running Docker application. Okay. So it's B. It is a read-only template containing a complete software application. It can contain more than one, but normally the spirit of things is to have a single application and have multiple containers, particularly if you make them really lightweight containers, like if you have the images are really lightweight based on Alpine, then it doesn't have an overhead, significant overhead to have multiple containers rather than multiple applications in the same container. And they can't interact with each other except through the network or possibly shared devices, so it's a good way of doing things. So now we're going to look at Docker images. So this is where the answer to some of the questions, how do you make a Docker image? Well, this is how we're going to do that. So Docker Hub is basically the repository for Docker images. It's maintained by the Docker people, and it's the default location for everything. So there's a number of base images there. They're typically based on a Linux distribution. So, for example, you can use CentOS latest. That can be used as a base image, or any other one that you might want to use. Say Alpine has an advantage of being very, very lightweight, very, very small. So what you then do is you build layers on top of a base image. And you can do that in two ways. You can either run the image as a container and then add the layers manually, or you can automate it using the Docker build process. And we'll look at both of those mechanisms. Sometimes you need to use a hybrid of the two. There's also a Docker search facility which searches for Docker hubs. If you go to Docker search CentOS, it'll give you a list of all the images which match the pattern CentOS, and you'll find that different distributions or different images, there will be several different hits from the search. Typically for, say, operating systems, Docker Hub has a kind of an official version. And then other people will store their versions of it on Docker Hub, because anybody can create a Docker Hub account and store their images there and make them searchable by other people. So if you search for something like Jenkins or Git or something like that, you probably find you get a lot of hits because you've got different people who have built them in slightly different ways. So if you're installing software, you can run your container and then you can install images using yum or apt-get, depending on which flavor of Linux you're using. Be careful about doing that. The first thing you often have to do is like an apt-get update. That adds all sorts of stuff that you probably don't need because it has to download all of its updated registry files. Also, yum and apt-get also pull in dependencies of any application, and you can get all sorts of stuff you didn't want. So to give an example that I wanted to install Java 1.8. I didn't want the OpenJDK, I wanted the Oracle version. If I wanted to install Maven using yum or apt-get, I was actually yum for CentOS, it pulled in OpenJDK 1.7, which I didn't want. And it just complicated things, added all sorts of extra layers which I didn't need. So I ended up installing Maven explicitly myself. So it's often easier to install software from tarballs or from direct RPM or .deb packages or archives, or just from files, than to use the packaging tools. Okay. If you're using Alpine, it's got its own package manager called APK, which is the equivalent of apt-get. So dealing with images. To list the images, do Docker images. That gives you a list of all the images stored on the local machine. If you want to get rid of an image, use Docker RMI, the name of the image, or the ID of the image. You'll find that you soon get a very large number of images, and you sometimes have to have a bit of a cleanup. So I recently did one of those and got rid of an awful lot of images I didn't want on my disk. So the base images. Okay, the CentOS base image is based on the CentOS operating system, but it isn't the full-blown system. So many commands are not there. So for example, none of the boot scripts or boot mechanisms are present on the image. You don't need them because you never boot a container. If you boot an image, boot something, it means you've got a kernel because you boot a kernel. And then that starts the rest of the system. You never boot a container, you just load it and run a program. So all that stuff will be missing. All the System 5 startup or whatever it is would not be there. CentOS, it doesn't have the which command or the ifconfig commands. So what you need to do sometimes is just install some of the basics and have your own version of the image, which has got some of the tools that you need. Curiously enough, I found when I was playing around with these things that one thing I really wanted was ifconfig, just to find out what the network looked like, because I was having networking problems. And so the first thing I had to do was a yum install -y nettools, because that's where the ifconfig command resides, in the nettools package. And the which command was also very useful for finding out where the executable was. So you may have to install things using yum for very simple things, but try not to install something which is heavyweight and going to pull in lots of unneeded dependencies. So here is an example using the interactive mechanism. You run the container, and if you do that, run -it, it's always a good idea to go -name to give it a sensible name rather than one of the auto-generated ones. So give it a name and then specify the image to start off with. Then I'm running the yum install commands. The run yum install -y. Yum asks a lot of questions. If you go yum install -y, the system automatically answers yes to every single question that yum asks. It's a very useful thing. There is actually a Unix command called yes, which just answers why. And it's used a lot to get around the problems of being able to automate and install from applications which keep asking you questions. So install the Witch and NetTools package and then exit the container. So the container's now stopped, but it's still on the disk and it's still got the Witch and NetTools software installed in the writable layer on the container. So I can use a Docker diff on CentOS, and that will show you the changes. That tends to produce a rather verbose output, which shows you every single file that's changed, and it's probably not that useful. Then I do a Docker commit CentOS net. What that does is it takes the container called CentOS and creates one of these read-only images called CentOS net with that writable layer now as a fixed layer on top of the image. Then I can quite happily go docker rm CentOS and delete it. So then I can do a docker run. Now --rm, as we saw in the exercise, that says delete the container when it exits. Don't leave it lying around. And so if you're doing something interactive where you don't want to keep it to do a commit, I strongly recommend using the --rm switch. I usually do it the other way around. Docker run -it --rm. And then you don't need to give it a name actually, because the name will go away straight away as soon as you exit. Then the name of the image, and then possibly the name of the command. You can use Docker inspect to see the layers. You get a JSON array back. It's very verbose and contains a lot of information. You can do a search on it, looking for certain strings in the JSON format if you want to look for certain things like architecture. But the Docker inspect is quite useful. It tells you all about the either the images or containers. Actually, it works on both. It'll tell you what the layers are in images. On containers, it'll tell you all about the networking and where the image was and all that kind of stuff. Well, that's all very well, but it's a bit manual. You wouldn't really want to do the interactive stuff unless you're trying to figure out how to do it. So the interactive builds that we just looked at, running the image to the container and then adding stuff manually, I tend to use that to find out how to do something. If I'm not sure exactly what the sequence of operations are to do something, I will do that to do a trial run. The best way to do it is to do an automated build. Now, this is important here. You need to have a directory of all the files required for the build. Don't have a directory with any rubbish in it there, because that can cause major problems, as I found out a couple of days ago. So what you do is you create a directory for each build, a separate directory. Then you create a file in that directory called Docker file with a capital D. And that Docker file defines the build process. And the directory with the Docker file is called the build context. So every single command in the Docker file generates a separate layer on top of the image. And how it works is this. It takes the base image, it creates a container from the base image, it executes the first command in the Docker file, it then saves the image, saves the container as another image, then it starts that image as another container, then it executes the second command, then it saves the container as an image, and then runs the image as a container. And it's a continuous sequence, so you can end up with a lot of layers added. Each line of the Docker file can create another layer in the image. There's a way around it to get the number of layers reduced, which we'll look at as well. So a Docker file, it has to be called Docker file, it's just a text file, and the first line should always be from, and that is the base image. It's the starting image, which you'll get from either the local machine or from Docker Hub or wherever else you want to specify it to come from. Optionally, you can give a maintainer and an email address if you wish to do that, if you wish to be identified with the image. And then you add a number of commands, and we'll go through each of the commands in turn. They don't necessarily appear in this order. Commands can be entered in several ways. Usually they can have the command followed by just a simple string, or the command followed by a JSON array, whichever form you want to use. So the first one defines the default shell. I typically don't use this. It must be specified in the JSON form. So in this case, we're doing /bin/sh-c is the shell, which is going to be used to execute all the other commands. Right, copy. When you run the build, you've got the context directory with the Docker file in it. Every other file in that directory can be copied into the container as part of the build process. So these source files and directories must be in the build context, which is the directory containing the Docker file. So in this case, I've got a file called jdk something.rpm. The star is just a wildcard. And what it's going to do is copy that RPM image into the /temp directory on the container. Okay. So once it runs that line, the container will now have that jdk.rpm file in its container. Destination directories must end in a slash, and they don't have to exist. It will automatically do an mkdir on the directory if it doesn't exist. Add copies files from the context or remote URL. So you can specify a full URL there, and that will copy them into the container. So in this case, I'm adding Apache Maven something.tar.gz into /opt. Now, this is an interesting one and a bit surprising. If it finds an archive such as a .tar.gz file, without asking, it will automatically unzip and unpack it. So what will happen is, in /opt, after that add command, you get the contents of the Apache Maven.tar.gz file, not the .tar.gz file itself. It's done automatically, a tar ZXF on the file to unpack it. Run is used to execute arbitrary commands. So any valid command within the environment that you've got will work. So run yum install -y, which, remember, must do the -y as it doesn't ask questions. Run rpm-i on the RPM file. That will unpack the RPM file, install it. Second one, I'm doing two commands separated by a semicolon, cd/opt, and then creating a symbolic link from the Maven archive to the name Maven. Each of those run commands generates a separate layer on the image. You can get around it by, in the Unix world, if you use the double ampersand to combine commands together, then you can get away with a single one. So you could go run yum install -y, which ampersand rpm-i, so on, ampersand, to produce a single layer from multiple commands. And you'll see that a lot in Docker files. Env enables you to set environment variables in the target image. So they'll end up in the etc. profile so that these environment variables are available. So this is setting the Java home and the path environment variables. And this will be the actual environment variables present in the container. How does the second command work? Run rpm-i /temp/star rpm. It basically installs an RPM package. No, I is install. Yep. Confusing, isn't it? Interactive install. Yeah. rpm-i. So this is set into environment variables. Command sets the default application. So that means that if you just run the container, docker run container image name, it will automatically execute the shell. Otherwise, you go docker run image name command name, and then it'll run that command, which overrides this one. Okay. So typically you have one command, cmd option, typically at the end of every Docker file to specify what the entry point is, and that normally runs an application. And then to do the actual build, you do docker build -t. Now -t is for tag, and that specifies the name of the image that it's going to build. So this is going to create an image called CentOS-Java:\latest in our local disk. Then the dot at the end specifies the directory, which is the build context. So that can be either dot for the current working directory, or it can be the name of an absolute directory or a relative directory containing a Docker file. So that's basically the process of building an image. So now we've got an example where we're going to use Docker to build an image, which is going to be an SSH server. We're going to have a lot of fun with the secure shell over the next lessons, because we have some interesting issues associated with keys. So if we have any problems later on, it's to do with keys. But this is going to build a Docker container based on an image, an Alpine image. Then it's going to install the SSH software, set up some keys, and then you're going to be able to run the container and connect to it using the secure shell. So that's the exercise. I think it maybe takes about half an hour. So as the usual, if you have any questions or when you're done, send a message to all participants, and we'll see where we get in about half an hour. This exercise, you have a number of things happen here. The one thing is you really do need to solve problems. It is very important, because if you're going to be a DevOps, you're going to have to solve the problems yourself with nobody to help you. It's always a typo. Copying and pasting commands can be very problematic, especially if there's something like smart quotes in there. But you've got the tools to do that. What you need to do is, if something fails, if it says cannot stat something, it means the file doesn't exist. That means you missed a step. So if you say cannot stat /ssh/idrsa.pub, it means you didn't do the SSH keygen step on step 2. So it's very important that you actually execute all the commands exactly, and it's actually worth typing them in to make sure that they're complete. So if something's, I mean, there are a couple of typos in the instructions, so I do admit that. But it is a matter of just going through each step. If you can't connect to something, it means the server doesn't work. So then you do Docker logs on the server and find out what's going on there. So probably if you can't connect to the server, it's because of, in step 3, in the contents of the Docker file, there's a few cases where there's a couple of smart quotes in the run SSH keygen, and in the command, the smart quotes. If you copy and paste the smart quotes, it simply won't work. Okay, so you just have to work it. What I will do is, I haven't got time to work on this any further because we've got quite a lot more to cover today. But what I will do is I'll fix all the typos in this document later today or early tomorrow, so you can try it again at some stage. Okay. I've got a note of all the things that needs to be changed. But it's a matter of trying to solve the problems, yeah? Great, yeah. Docker build, but you're missing Docker build -t label space dot. That is, the space dot is very important, okay? It must be a directory. Yeah, absolutely. Research and development is great. Just check things out, because basically one of the most important things, if you're going to be a DevOps professional, is you've got to be a problem solver. And you're going to hit all sorts of problems in the real world, and they're going to be difficult to solve. You'll do a Google search, you will not get a sensible answer. And it's a matter, I spend most of my time trying to get stuff working, simply because the documentation for, say, Docker is absolutely appalling. Most of it's just wrong, it's out of date, and doesn't work. You do a Google search, and you just get more problems. It's a matter of doing the be able to problem solve. No, you don't need to add anything to the commands of the Docker file. You just put them in as they are with there's a few quotes that need to be changed, but otherwise the commands. Yeah, when it says add authorized keys, it means it's expecting to find a file called authorized keys in the build directory. And in a previous step, you actually copied the public key from the SSH directory to a file called authorized keys. That's where it came from. You don't have to add anything to it. It's just literally as it states in the instructions. Yeah. Okay, great. It's a difficult business. It's tough, and it's getting worse. I assure you that I'm getting increasingly worried about the internet because the signal to noise ratio of the internet is getting much worse. So if you want to find something about the private life of a celebrity, you get it as Google search will give you all the information, all the gossip you need. If you want to find how to do something in software, you're going to have a challenge because most people don't know the documentation that's there is going to be out of date or missing or just downright wrong. That's the biggest challenge you actually face. It's the biggest challenge I face. It's quite interesting to work around it, but okay, I've got to solve this problem, and it can take a long time. So, but welcome to the real world. It's this is just the way it is, yeah. So, but yeah, typos are the worst, and the error messages from the system tend to be very bad, don't they? They're not very helpful. Something didn't work. Okay, so what? What happened? Yeah, that's exactly the problem. That we're living in an increasingly difficult world to operate, so you need to be a good problem solver and have a good way of around how do I solve a problem like this? You know, give it a try. Yeah, by all means, and no one do this. Retry the exercises tomorrow and just spend a little bit of time thinking about, okay, I've got an error. What is it? What caused that error? Because that's where you need to be ultimately to be a DevOps, because that's what it's all about. So, but it's fun because it's a challenge. You have to, and when you get the answer, when you get it working, it's a good feeling, isn't it? Oh yeah, great, I've got this working. Okay, and solve problems for other people, which is effectively what you're going to be doing as well. It is true. Yeah, absolutely true. Absolutely true. You already no, unless you've already encountered this, haven't you? It's a little frustrating sometimes. Yeah, I've spent half a day wasting my time trying to get something working, and it was a stupid little reason, like there was a missing quote or something like that. But yeah, you'll get there. I'm sure you'll get there. That's a good challenge on the course, isn't it, to solve the problems? And I've noticed it's good that some of you are helping the others, which is really great, because that's another part of it, is to help each other when you get a problem. Some of you have solved it. Some of you get a bit stuck. It's no problem. It's all the part of the learning process. Docker, you don't tend to have user interfaces on Docker because user interfaces require a lot of code. And how do you connect to it? Okay, what we are going to do is connect our virtual machines, the ones you've got on the Google Cloud Platform, via VNC, so you'll be able to collect from a local client. But typically, yeah, keep it light. Absolutely spot on, Roshan. That's absolutely right. Docker containers should be very minimal servers which don't do an awful lot. You don't want a graphical environment. There might be a web server inside there, and in many cases there will be, because most applications like Jenkins and even Docker itself have got web front ends to them, or REST front ends. So you can access the containers via a web interface. Absolutely, you're spot on. It's to get the job done. It's not for ease of use. You've got to. You're not going to get an easy life. You're not going to get a nice, fancy user interface. In fact, with Google Platform, I was talking to my friend Randy yesterday, and the graphical user interface, the UI, keeps changing, but the command line tools don't. So what he does, He always uses the command line tools and scripts everything. And so it always works. Okay? The user interface is unreliable and messy, whereas the scripts always work. Okay? And that's one thing when you're doing sort of operations work, and that's what I did when I started doing administration work for a mobile phone company. I spent most of my time for the first few months writing scripts so that I could totally automate everything. Expose 22 exposes port 22, which is the port that SSH listens on. Yes, you have to be good at writing things. You need to be a good script writer. Yeah, absolutely. Absolutely. You need to know your Linux commands and your bash shell scripting well. Otherwise, your life's going to be very difficult. You're going to have to end up typing an awful lot of stuff. Because a lot of the commands are quite long. Absolutely right. It's a good learning exercise. What Docker run minus P does, it's Docker run minus P number : number. And it says basically it's like, yeah. No. The expose 22 says expose port 22 to the outside world. The Docker run minus P 2022:22 says when you run the container, map port 22 on the container to port 2022 on the local host, which means that you can access the container via a local port. Any suggestions how to learn shell scripting quickly? Take a shell scripting course. It's quite complex. Yeah. Because shell scripting is actually more difficult than you think. The shells like Bash and the Corn shell are very complex, and they're actually a complete programming language in their entire right. You can do all sorts of amazing things in the shell if you really know what you need to do. Like, for example, you never need to use awk if you know the shell. Good point. Yeah, have a Linux distribution available in a virtual machine or on a separate machine or something like that, and just play around with it. But writing shell scripts is actually quite hard because there's a quirk of the shell scripts that the presence or absence of a space can make a big difference in whether the script works or not. And it's that bad. Okay. Okay, so let's move on to the next bit because we've got other things to come. So why do changes have to be made to containers rather than images? Images are read-only, containers have a writable layer, containers can run programs, or all of the above. The SSH minus P2022 changes the port number from 22 to 2022. Okay. We're getting some answers. So the correct answer is D, all of the above. Yeah, that's what it's all about, guys. Working together, help each other, because everybody will trip up over a step and it'll be not obvious why. Yeah, make sure you've got no typos in things, and typos are not easy to spot until you get trained. I mean, I've been in the training business a long time, and I'm very good at spotting silly little typos, which can keep people puzzled for hours. But that's something you need to acquire as the time goes on, the ability to spot those little things like that missing double quote or that double quote's a smart quote. But it's all good. You get there. So, registries and repositories. Okay, so let's have a look at these. These are the important things about where you store images. So basically, where do you get the images from and how do you get them in the right version? Okay, and so Docker uses registries for doing this. And registries can exist in various places. They can be hosted by various organizations, or you can create your own if you wish. And you need to think about where it needs to be in security, who needs to access your images. So a registry is a very strange name. A registry is basically a server, typically a web server, where images are stored. And every image has got a name. So the registry managed by Docker are stored in repositories. Now, a repository is something a little odd. A repository is a collection of images of different versions. So you've got the registry called Docker Hub. Then you've got, say, the repository called Alpine. And in the repository called Alpine are all the versions of the Alpine images that Docker Hub supports. Okay, so remember, a repository is a collection of images of different versions, usually including latest. And the tag describes exactly what the image is. So the tag is the name of the image, if you like. So actually, when you talk about an image, it's actually got several different names. So if we talk about NGINX, which is a web server, you can go Docker pull NGINX. That'll give you Docker NGINX :latest. You go Docker pull NGINX :1.9. It'll get you 1.9. You can also go Docker pull hub.docker.com/_/NGINX :1.9. That'll give you the same thing. Basically, it defaults to Docker hub.docker.com/_/ followed by the name, because Docker Hub is the default. So you can see the full name of it is actually a domain name, a URL, followed by a path name, followed by the actual registry. So the labels, which are the full names of the images, are basically URIs. They look like them. They really are. So it consists of a fully qualified domain name of the registry, which defaults to Docker Hub. The namespace, which is _for Docker Hub and R for user, anybody else. Then the repository name, which is really the image name, okay? Sorry, you can also have the organization name. Then you have the repository name, which is the actual image name, and then you have the version number afterwards. So we've got the URL looks like that. We've got hub.docker.com/R for repository, /databliss is the name of the user or organization, netkernel-se is the name of the image, and then after that you can go :version number if you wish. So Docker Hub isn't the only one. There's the Google Container Registry, part of the Google Container Platform. Amazon has got one for AWS. There's Key has got free ones, and you can also set up your own private ones as well. Now, a lot of these registries like automated builds. So what happens is this. You set up an account with Docker Hub, say. You also set up an account with, say, GitHub, the Git repository for source control. Then you connect them together. Then what happens is, every time you make a commit, your Git repository will contain a Docker file and any other files. Every time you commit to the Git repository, Docker Hub will check out that commit and generate a new image by using a Docker build. And this is the preferred solution, and actually you may need to do it that way. So it's an automated process. You commit the Docker file, it builds an image for you. You don't have to build the image and upload it. So to set up a repository, you need to have a user account with Docker Hub. You need to log in, create a repository, give it a name and all that sort of stuff, a namespace and everything. Set its visibility and create it. And then you can put the Docker file in there and everything works like fine. To log into the registry, you do a Docker login and specify your username, and that will log you into the Docker Hub account. It'll store your username and password in a file in your home directory called docker/config.json. So the images need to be the same name as the repository. And so what you can do there is you can create an image from giving it your name. You can commit the image and give it a name. What you have to do there is basically the name of the image must be the repository name / the image name. And so you must make sure that the image name matches, which is the tag, matches the name of the repository. So if you create a repository with a certain name, then you must make sure that you rename it by doing a commit or a tag operation. You can retag the image to make it have another name. You'll see how this works in detail later on. And then you pull it using the full name. So that's effectively pulling something from Docker Hub. It's got an implicit hub.docker.com /r/, then it's the username followed by the image name, possibly version number. And that's the other thing, the version number can be more than just a number. In this case, I've got an image called question, and the label is Java-1.0. So it's not unusual to have, say, I've got an image called Alpine, and I'm going to call the image Alpine:/SSH, which is Alpine plus SSH, and you'll find that notation is used quite a lot on Docker Hub as well. You can delete images by giving them the full name, just as you can before. Private registries are if you want to store images, you don't want to put them in Docker Hub or somewhere else. You might have to pay for them, or you want to keep them local. You might want to keep them secret. Deal with things for various project life cycles. So if you want to have a private registry, you can do that. There's several ways of doing that. There is a Docker container called registry, which contains a Docker registry. So if you do Docker pull registry, you'll get yourself a Docker container containing all the code to implement a Docker registry. And then what you can do is run that registry as a container. And we're using the -p option here to map a container port to a host port. This is a key aspect of networking in Docker. The actual container is listing on port 5000 here on its local network, which you can't get to from the host. If you do the -p, it creates a port on the host which is mapped to the port 5000 on the internal network that Docker maintains. That's how you expose containers to the outside world, by effectively making them listen on ports on the local host itself. So using the IP address of the host, you can get to the container via the port number. So once that's done, you specify the registry as the host name :5000, in this case it's localhost. And so now what we can do is we can pull an image called Alpine, which is going to give you the Alpine from the Docker Hub. The tag basically creates a new image with a different name. So we're calling Alpine:/latest localhost :5000 /Alpine:/latest, which means that this image now belongs to that new registry on localhost :5000. Then you can push that image onto the local registry. That's how it works. So remember, the registry name is part of the label, unless it's on Docker Hub where it's by default. Now, if you want to configure the registry, which you normally need to do, it's configured by a YAML file, which are always wonderful. What you can do is override the configuration file by putting a config.yml into a directory. What that -v switch is doing there is it's mounting a local file called /data/config.yml onto /etc/docker/registry/config.yml. And that means it'll use that configuration file to configure the registry, because that file will override the existing config.yml file in the default image. So external configuration is always required. Typically, you need to have external storage, because if you delete the container, you lose all the images. We'll look at Docker volumes later, but the configuration files are quite complex, and there are sample configuration files in the Docker Git repository. There's also an RPM package available for Red Hat Linux, like Enterprise Linux, Fedora, and CentOS. And if you install the RPM package, it will implement a registry in a container or on a host machine. and it uses a Python program called Unicorn, Green Unicorn, which is a Python-based HTTP server, which gives you basically web server functionality, because the registries are actually basically web servers with the images underneath them. So if you want to install a registry on a standalone computer rather than a container, you just install the Docker registry package onto your Red Hat-based Linux machine, and then you change the registry.yml file to configure it, then you restart the registry, and that's it. You've got yourself a Docker registry on a local machine. If you want to do it in a container, it's slightly more complex because you haven't got any boot scripts. So what you need to do is write a shell script which starts up the gunicorn web server and configures it with the registry. So basically this rather messy looking script will enable you to run the RPM package-based registry in a container if you want to do that. So to do it in Docker container, you pull a RPM image such as CentOS, you add the RPM using either Docker file or manually, and then you change the configuration file, replace it or edit it, and then you install the boot script, that complicated thing, in a suitable place, and then create the new image from that. And then you've got yourself a registry image in a Docker container. Then just run the container. It's always a good idea when you build a container, an image, to run it as a container with the bin/bash to start with, so you can check everything's okay. And then once that's all up and running, you start it up. This is actually starting the registry manually. And then you can try doing a Docker search on the container, try and pushing an image on the container and checking that the image is actually in the container. Okay, so that's the Docker registries. So now we've got an exercise to do this: pull the CentOS image, start as a container, install the registry, and run the registry and push an image into it. So now you're going to need a URL for doing this. This is the URL. Okay, and so we'll probably be about half an hour on this. So let's do the same thing. Tell me when you're done. If any problems, post it, and try and help each other out. Try and solve some problems, because it's a tricky business. Okay, so I'll speak to you soon. Okay, so that was a much more straightforward one. This interesting thing about copy-paste, the problem is that certain word processing tools like Word and PowerPoint and the other ones in Microsoft, what they do is they replace certain characters with strange characters that don't really exist in the IT world in terms of Unix. The classic ones are the smart quotes, where instead of having double quotes, which are just both the same, you have the kind of 6s and 9s. And also, if you type minus in any Microsoft product, it turns into this horrible long vertical bar thing, which is not a valid code in ASCII and will not work under any circumstances in Unix. And what happens is you use these tools and those codes get copied and pasted into your application, and the codes actually are valid characters, but the Unix command doesn't understand them. That's the problem. It is a big problem, actually. It really annoys me that using sort of like PowerPoint, I type minus and I get this stupid long bar thing. In fact, I've actually now, in conjunction with a colleague, we've decided that we're not going to use Microsoft products anymore for any documentation. We're going to use LaTeX, which is a very old program, but it actually does do it properly. And we're not going to use PowerPoint. We're going to use LaTeX for presentations, because it doesn't do those stupid things to the characters. So yeah, in some of the instructions, we've got smart quotes and we've got these silly minus sign characters which don't work. So there's nothing, you can't really beat some kind of doing things manually. No, it's not really a font issue. It's actually that by default, the Microsoft products like PowerPoint and Word have these autocorrect facilities. Unless you switch them off hard, they will try and convert certain things so that if you use a single quote, it likes to use the back tick and the front tick. If you use a double quote, it likes to use the 6s and 9s characters. Nano's just another editor. No, VI, you can guarantee, is always going to be there. If you're going to use Unix, which you probably almost certainly will be, you really need to know VI. You don't need to know every single command. You can learn one new command every week for the rest of your life, maybe. But as long as you know the basics, you'll be fine. But VI is just the standard text editor in the Unix world, and you can guarantee it's going to be there. Nano is another one, which may or may not be there, depending on the distribution you've got. So in terms of text editors, yeah, VI is the one, unfortunately, but there's some great VI cheat sheets you can download and print out, which tell you what the basic commands are. But you can actually use VI in a very simplistic way. All you need to know is the insert and command modes, and then just use the arrow keys and delete and type. Okay, so that's Docker registry, where we created a registry there. So we have now the knowledge check for this one. How can you determine which repository an image comes from? Okay, you have a number of answers there. Oh, quite a few different answers there. Well, the answer is A. The repository location is contained in the image label, and if there isn't an image label, it defaults to Docker Hub. Okay, so we've got a very short section here on Docker Machine, which is used for managing remote Docker instances. So what is Docker Machine? It's a management tool for dealing with Docker hosts. So the idea is that you've got a network of machines, which may be local or on the cloud, and you use it to administer them. What you do is you designate one particular machine, one computer, which is the management machine, and you install Docker Machine on it. You can also install Docker daemon and client on the same machine if you want. It's entirely up to you. But it was only available on Linux for early versions, but now it's available on other systems such as OS X and Windows. So what it does is it controls other hosts and enables you to install and maintain Docker on other machines. It's a great idea. You just have a central location where you deal with that. So what do you use it for? Well, one thing is to run Docker, install Docker on remote hosts. You can actually use it in conjunction with the Docker toolbox on virtual machines as well. In fact, the original versions of OS X and Windows required Docker Machine, because if what you did was you ran the Docker daemon in a virtual machine and you need to be able to administer it, and you could only do that from the local machine by using Docker Machine itself as a tool. So Docker has components. Docker itself is really Docker Engine. It's the Docker daemon, which has a RESTful API and the command line client. That's basically that part. There's also Docker Machine, which is itself a separate executable. It may come with the actual Docker install. It might be separate. Some of these components are actually separate downloads. But Docker Machine has its own command line client called Docker Machine. If you install that, it also has a Docker client. So you may need to install it separately, or it may come with your Docker installation. There is actually another one called Docker Compose, which is really bizarre. For most distributions of even Linux, you have to download the binary independently of everything else, which is rather odd. So Docker machine has the means where you can create a Docker installation on a remote machine, which is a rather interesting concept. It's not perfect by a long way. I had a few problems, but it does actually work in principle. So what it does is it allows you to install Docker on a remote machine. First of all, you need to set up a few things. And the first thing you need to think about is security. Now, SE Linux, SE Linux is Security Enhanced Linux, which is an extension to Linux, which was instigated by the NSA in the USA, the security organization. The reason for it being is that in the Unix world, root is all powerful, and that was considered bad from the security perspective. So what they did was they installed the SE Linux, which changes the way the rules work. So basically, root isn't all powerful anymore, because SE Linux can stop anybody from doing anything, but it can have some very strange effects. I had an experience a while ago where I installed Linux on a bunch of machines and wanted to exchange mail messages. And we couldn't send mail messages. Why not? I looked at everything. All the servers were running on port 25. They were listening on the external IP address, and yet we couldn't send mail messages. SE Linux blocked it. So the first thing to do is switch SE Linux off. And you can do that by changing the file SE Linux, etc/SE Linux/config, and set SE Linux to disabled and reboot, and then SE Linux goes away forever. But also make sure that there are no firewall rules blocking the ports. By default, many Linux installations have firewall rules on the input chain which block external access to certain port numbers. You may need to switch those off, otherwise it's not going to work. You also need to have sudo access on the remote machine without password. It looks sounding a bit like a security nightmare, isn't it? We switch off SE Linux, which is a security system. We switch off password-protected sudo access to root on the remote machine. It's not looking good, but we have to do it. So what you need to do is edit the etc. sudo as file and grant no password access to maybe a single user, which is the one that you're going to use for Docker. Not everybody in this case, as in this case, I'll make it a bit more restricted. And then what you need to do is have SSH access with no password. Another security issue. Getting a bit worried about security here, and this is not the worst of it. So what you need to do is, first of all, generate a pair of keys, which you did actually in an earlier exercise. SSH keygen minus TRSA generates a public-private key pair. And what you need to do is copy the public key from the local machine and append it to the authorized keys on the remote machine. The authorized keys file in the SSH directory on the remote machine contains a list of public keys of users on remote hosts who are allowed to connect without a password. Then what you do is you copy the key to the remote host, append it to the authorized key files, and then you've got complete access. And then you can install Docker remotely. This enables you to access a machine which has already got Docker installed, where what you specify is the machine's IP address and the name. And basically, Docker machine needs to be able to manage all remote machines. So it needs to be told about them. You either do it by create, where you tell it about an existing one, or you do a create with a different set of parameters where it actually creates a Docker instance on the machine. And then you can do a Docker machine ls on your Docker machine, the one that manages everything. Do a Docker machine ls, and it'll list all the remote machines that it knows about, all the machines it can manage. It needs a number of drivers. There's ones for the various cloud ones like AWS and Google Cloud Platform, and they allow various things to be started and stopped, and it's very powerful stuff there. So you got the AWS, Amazon EC2, and the GCE one for Google. So you've got the Docker machine drivers enable you to install machines remotely. Now there are some issues. So, for example, with CentOS, I use Docker Machine to install Docker on CentOS, and there's a boot script missing, a rather important one, which was the one that did the port listening. So I had to manually add it before I did the install to make it work. So it's not perfect. The support of Docker for certain flavors of Linux is not complete. They seem to favor Ubuntu Linux for some reason, which I really don't understand. I personally detest Ubuntu because it's based on Debian, which is actually a very good distribution, but they've done some horrible things to Debian, and Ubuntu got a popularity which I really don't understand, because if you go into the covers of Ubuntu, it's absolutely appalling. The boot system is completely messed up. That's my personal opinion, but I think they have made a complete mess of Ubuntu. So that's the knowledge. Now we have the knowledge check for this. So what security issues can affect Docker machine operation? Yeah, A, B, and D work. Yeah, it can be blocked by SE Linux and firewall rules. It does require password-free SSH and sudo access. So those two things are a little bit concerning in the security sense of the world, but actually it is D, A and or B above. Okay, so key takeaways. Virtualization is a great thing. It enables you to have different computing environments which are separated and isolated from each other, rather than to have to deal with all the dependency problems and issues. The Linux kernel has been enhanced in wonderful ways to enable container virtualization to happen. Docker is a very powerful tool. It's got the concepts of images and containers. It's not the only one. You can also use LXD and Rocket. Docker images is constructed by adding layers to a base image. It's always image, container, image, that kind of structure. Registries manage repositories of images. Remember, a repository is just different versions of the same image. It's a little confusing because repositories mean something different in the context of, say, source control, where a repository applies to an entire project. And Docker Machine allows Docker to be installed and managed on remote machines. So now we have the quiz. So quiz 1, what is Docker Engine? Okay, this is looking good. It's the daemon, the client, and the RESTful API. It's just referred to as Docker or the daemon or the client, but it's basically the basic core stuff that works. So what is Docker Machine? Okay, shouldn't have consecutive answers with the same answer, should I really? It's I guess a little confusing, but yeah, it's C. It's software to remotely install and manage Docker installations. So, quiz C, what is container virtualization? Okay, yeah. It's the operating system level virtualization, which are standalone applications controlled by a single kernel. So what is a union file system? Quiz 4. Okay. Yep, it's a file system which can be assembled in layers. It's very important for the concept behind this containerization. And quiz 5, what is a Docker registry? Some different answers there. It's B. It's a service for managing remote repositories and images. Okay. So that's the end of this section on virtualization and lightweight containers. The next lesson, which is going to be next Saturday, is on data storage and access. So we're going to be looking at various types of databases and big data and the importance of data. So a couple of things to go for the, oops, I'm going to go back. So I think we learned a lot today. I think as we see, getting things to work is actually quite difficult. And I think that one of the biggest challenges for DevOps, I think, as we've seen today, and yesterday, in fact, is that many of the tools are quite hard to configure, and you have to do it command line. You don't have fancy GUIs, and you need to solve problems. So that's one of the biggest challenges. Remember we talked about the cultural changes in DevOps? So we've got a break of a week. I strongly recommend if you've got time to just work through some of these things and do some research, try and make sure you understand things completely, because we're going to go build on what we've done over the next few weeks until we get to lesson 8. So it's all good stuff. But so now, question and answer. Have you got any questions on anything from today, yesterday, future, or in general? Yeah, the expose keyword is actually not necessary. When you do the Docker run command, you go -p local port remote container port. So yeah, you don't have to do the expose command. It's not necessary. It probably was there, but it's not necessary. Any other questions? Yeah, good question. The slides are online. If you go to the LMS on the Simplilearn website, you have the login for that. If you remember the very first presentation done by the host, she pointed that out. So you've got the ebook, which is basically the slides. You've got the URLs for the courses. Just basically to get to you've got the URLs, yeah, and you just try them out, rework things, try a few of the commands, look at some of the other things that you can extend. Okay. The videos from the WebEx session from today will be available in 24 hours, I believe. The ones from yesterday should be available now if you want to access them. Can a Windows client be put on Docker? You can install Docker on Windows if you've got the right version, or if you use the Docker toolkit. I think there are some Windows images you can use. Problem with Windows is it's all licensed, and the other way. What do you mean? Okay. Putting Windows in Docker, I'm not sure you can do that. It doesn't really make any sense, because what happens is Docker images are actually just partial file systems. They're not operating systems. Okay, you've got the support people if you want to contact them. Say in the break, which is the week between now and Saturday, if you can practice anything you don't quite understand or have problems with, why don't you do so? Now, if you want to start an Ubuntu container and access it from PuTTY is basically SSH. So if you do the exercise where we installed the SSH server or using a Ubuntu container, make sure the SSH server is running, then you can access it from PuTTY, because PuTTY is just an SSH client. All the apps available as images on Docker Hub, massive amount. Just go to dockerhub.org and just scan it. It'll show you everything that's available, and there's a huge number of images. Every single popular flavor of Linux with all sorts of combinations of things installed on it. So yeah, I mean, if you want Jenkins there's Jenkins. If you want a web server, there's Apache, there's NGINX, there's all sorts of stuff there. So do play around with it. Pull the images down and try them out. A lot of the images in Docker Hub work in two ways. That they basically, you pull the image, and there's usually documentation associated with them. If you read the documentation, you'll find that you can set certain options on the command line when you run the container, which configure it. And you can do some really good stuff. So basically, images are more complex than it appears. It's not just build the image, run the image. It's actually build the image, then it runs a script which enables you to configure the image and then run the image. So it's quite complex. Okay, so make the best use of the break. There is a help and support. The evaluation form will appear when you check out. And thank you very much for attending today, and look forward to the next session next Saturday, the usual time. Thank you.